Hello and welcome. This is World of Wastewater, and you're watching part 19 in a series going over a wastewater exam that you can find a link to in the description below. If you're following along, these questions are numbers 91 through 95. Hit like and subscribe if your treatment plant runs on these three things: bugs, bubbles, and people pretending they are not stressed. With that said, let's get started. Filamentous bulking of activated sludge may be controlled temporarily by A. Adding sodium chloride to the aeration tank, B. Spraying water to reduce foam on aeration tank surface, C. Chlorinating the return activated sludge, D. Adding a polymer to the final settling tank. The answer is C. Chlorinating the return activated sludge. Let's talk about one of the most common headaches we face in wastewater treatment: filamentous blooms. When your SVI is rising and your sludge isn't settling, sometimes you need an emergency brake. That's where chlorinating the return activated sludge comes in. I've outlined on the screen why this works. The healthy flock-forming bacteria clump together in a cluster, or flock, but the filamentous bacteria stick out from that ball like the little hairs on the skin of a kiwi. Because those filaments are exposed, a dose of chlorine will burn them off. The dose of chlorine should be low so that it doesn't penetrate deep enough to kill the good bacteria in the flock. It's a matter of surface area. The chlorine prunes off the bad stuff without harming the good core of our biomass. However, it's important to understand that chlorination is just a band-aid, a short-term fix to get your settling back under control so you don't violate your permit. But if you don't stop the chlorine without fixing the underlying problem, those filaments will come back and keep causing problems. To truly solve the problem, you need to figure out what caused the filamentous bacteria to take over. It could be an internal process issue, like the dissolved oxygen being too low or the food to microorganism ratio being off. Or it could be coming from outside of your system, from an industrial discharger sending a slug of grease or high sugar waste. Or it could be something toxic that is shocking the system. Until you adjust your process or work with those upstream dischargers to control what they send you, you're just treating the symptom, not the disease. Use the chlorine to survive the bloom, but use your data to stop the next one from happening. Which analysis provides the most immediate quantitative indication of toxicity affecting the biological activity of microorganisms? A. Chemical oxygen demand, B. Effluent turbidity, C. Microscopic examination, or D. Specific oxygen uptake rate. The answer is D. Specific oxygen uptake rate. One of the best techniques for detecting and tracking your plant's performance during a toxic event or overloading of nutrients would be to perform a SOUR test, which stands for Specific Oxygen Uptake Rate. This test measures the actual metabolic rate of your microorganisms, which is like the breathing rate of your bugs. This is advantageous because it gives you a hard number to track how well the microorganisms are performing over time. For example, when people are sick, they don't work very well. Similarly, if the bugs in your aeration basin are under the weather, they won't do their job well either. The SOUR test will let us know if the bugs are healthy by giving us a number value to assess how well they're performing. As an operator, your best tools are often your own senses. Once you're familiar with your plant, as you're doing your rounds, you'll notice when something's off. It might be an unusual odor in the air near the headworks, or maybe the mixed liquor in the aeration basin looks darker than usual. Your eyes and nose are telling you there's a problem. But to fight the problem, you often need to know how bad it is and exactly how it's affecting your plant. You'll likely need to interpret results that only lab analyses can provide. What I'm trying to get at here is that oftentimes operators are going to use both qualitative and quantitative assessments to troubleshoot and fix a problem. With this question, it's important to pay attention to the wording. It asked what the most immediate quantitative indication was. So while choice C, microscopic examination, is a great qualitative way to check on your plant's performance, that answer is there to trip you up. I'd like to note that microscopic examination can be used for quantitative analysis, but we as operators typically only use them for qualitative analysis. So the SOUR test, which provides a quantitative indicator, is the best answer to this question. Calculate the food to microorganism ratio using the data on the screen. A. 0.76, B. 0.23, C. 0.42, or D. 0.86. The answer is D. 0.86. Now it's time for everyone's favorite part, the math breakdown. The food to microorganism ratio, commonly referred to as F to M, is a measure of how much BOD is coming into the plant in relation to how large the population of microorganisms is that we have in our system, which we measure as mixed liquor volatile suspended solids, or MLVSS. The formula is simply the pounds of BOD per day divided by the pounds of volatile suspended solids in the system. So first we have to calculate the food, or the pounds of BOD entering the aeration tank each day. To do this, we use the loading rate formula. So we take our flow of 9.7 million gallons per day, multiply it by the BOD concentration of 240 milligrams per liter, and multiply that by 8.34 pounds per gallon. This gives us a total of 19,415.5 pounds per day of BOD. That's the food part of the ratio. Next, we calculate the microorganisms, the total pounds of MLVSS we have in the aeration tank. For this step, we use the mass formula, which is essentially the same as the loading rate formula, but the units are slightly different, so we get an answer in total pounds, not pounds per day. To do this, we take the aeration tank volume of 1.5 million gallons, multiply it by the MLVSS concentration of 1,800 milligrams per liter, and multiply that by 8.34 pounds per gallon. This gives us a total of 22,518 pounds of MLVSS. This is our microorganism value. The final step's the easiest. Divide the food by the microorganisms. We take our food value from step 1, 19,415.5 pounds per day of BOD, and divide it by our number from step 2, which was 22,518 pounds of mixed liquor volatile suspended solids. And that gives us our final answer, 0.86. Which of the following routine maintenance activities is typically performed most frequently to ensure the continued optimal performance of a UV disinfection system? A. Replacing the UV bulbs. B. Cleaning the quartz sleeves. C. Flushing the chambers. Or D. Power cycling the system. The answer is B. Cleaning the quartz sleeves. Here's the simplest way to think about it. The UV lamps are protected by clear tubes called quartz sleeves. You can think of it as a shield for a light bulb. For the UV system to work, its powerful ultraviolet light must pass through these sleeves to reach and inactivate the pathogens in the effluent so a plant can meet its disinfection limits. Just like how hard water stains appear on shower doors, over time, minerals and solids in the effluent build up on the outside of these quartz sleeves, which we refer to as fouling. This fouling blocks the UV light, basically putting a shade over your lamps. If the sleeves are dirty, the system isn't reducing pathogens effectively, no matter how powerful your lamps are. While you eventually have to replace the UV bulbs, they have a lifespan of thousands of hours, so you don't do it very often. But keeping those sleeves clean is a constant and critical task. Many modern units have automatic wiping systems to help with this task, but that doesn't replace the need for frequent inspection to maintain optimal performance. Also, I'd like to give a quick shout out to Trojan Technologies for providing these great images. I have a link to their website in the description if you want to learn more about their UV systems. SVI is calculated by using the results of which pair of tests? A. BOD and TSS, B. TSS and OUR, C. SSV30 and MLSS, or D. BOD and MLSS. The answer is C, SSV30 and MLSS. SVI stands for Sludge Volume Index. In simple terms, it's a measurement of how well your sludge settles while accounting for the biomass concentration. Before you can calculate the SVI, you have to perform 2 separate lab tests, both of which likely already get run every day at your plant. The first test is the 30-minute settled sludge volume, which is conducted using a settleometer. You grab a sample of your mixed liquor, let it settle for exactly 30 minutes, and read the volume the settled sludge blanket takes up. Your result is in milliliters per liter. The second result needed is the solids concentration of your mixed liquor, better known as mixed liquor suspended solids. This is a standard lab test where you filter, dry, and weigh a sample to find out how many solids are in your mixed liquor. The results for this formula will be in milligrams per liter. If you're asking why the equation says times 1,000, that's because we have to convert the units to milliliters per gram, not per milligram. So what does the sludge volume index result mean for you as an operator? A good SVI is typically between 80 to 150 milliliters per gram. This means you have a good, healthy flock that settles well and compacts nicely. A low SVI, generally anything under 80 milliliters per gram, means your sludge is too dense and it settles too fast. In this situation, you may also end up with high levels of pin flock, which doesn't settle well and can cause high effluent turbidity. A high SVI, anything over 150 milliliters per gram, is a warning sign that your sludge is bulking. This is often caused by having too many filamentous bacteria in the system. It means your sludge is light, fluffy, and takes up a lot of space relative to its concentration. This is a huge problem because it settles slowly and can wash over your clarifier weirs, resulting in a permit violation. So to wrap up, the SVI connects your 30-minute settleability test with your mixed liquor suspended solids concentration. It's the single best number for tracking your sludge's physical condition. SVI is one of the most important process control numbers that an operator uses, and it's very likely you'll see a question about SVI on your exam. Hey, thanks for watching. If you enjoyed this video, then check out the others on this channel. If you want to help us keep making great content for operators, there's a link to donate to World of Wastewater in the description below. See you next time on World of Wastewater.